walk out.
I mean, he's the father of radio astronomy. Maybe I should say grandfather now. So there are now grandchildren around. And anything that you can think of, I think he has been awarded. But probably one of the important things is being a fellow of the Royal Society, and also some. If I have to name all the awards, then I will spend the next 1 hour in this. So I asked him after we decided that to get him here, what would you like to talk about? And I gave 2 choices, maybe radio astronomy, history, and all that. And I think typical of Govind, he wanted to talk about some new work that he's interested in. He doesn't want to tell you stories like a grandfather. So I'm absolutely delighted, Govind, that you want to talk about this. The observations with GMRT about Venus.
I'm delighted to give this talk. Kandu got hold of me. He insisted I must talk. He wanted to talk to me about genesis of radio astronomy. I could have talked on that. And Bakchi and other wants to put it on the YouTube. That could have gone, okay, YouTube. But not this. Because this is still preliminary work. This is my plan of the talk. Venus overview, measurements made by Russian Venera lander to the surface of Venus, radar and radio observations of surface of Venus by NASA Magellan orbiter, exploration of the upper atmosphere, Venus by Venus Express, microwave observation by the VLA, GMRT observations, radiation transfer to explain GMRT observation. Venus, because of its thick atmosphere, the surface of Venus cannot be seen optically. Its atmosphere has been probed by more than 30 spacecrafts over the last 30-40 years. The atmosphere of Venus consists of 96% of carbon dioxide, 4% of nitrogen, and some amount of traces of sulfur dioxide, etc., whose content varies across the atmosphere to troposphere up to 60 km height to mesosphere. Since CO2 is a very efficient greenhouse gas that we know on Earth also, the surface is very hot, 735 K, and its temperature does not have diurnal or pole variation. So you cannot go and land like on Mars and so on to figure out what the surface is. You have to do probing. Well, Venera did, as I described to you, Russians did land there, but it lasted only for a few hours because of the high temperature. They didn't know at that time. Because of high temperature, surface has been explored only by Russian Venera lander and found that the surface is similar to that of terrestrial basalts and granites. Radar echoes and radio observations have been detailed probing of the surface, particularly by NASA Magellan orbiter, radar echoes, passive radio wave observation, and VLA and GMRT. This is the image of the, which I got it from Google, of images of Venus from Russian Venera landers. I don't quite understand all that is what is there, but the image says, but the paper says that the Venera 1314 shows a very flat landscape. Basaltic rock and soil dominate the landing site. That is similar to the Earth, basalt and granite. They give some data on that. Mariner, Pioneer, Venera, Magellan and Venus Express. The Mariner, Pioneer, Venera and Magellan missions during 1969 to 72 provided detailed atmosphere, detailed description of the physical and chemical condition in the atmosphere of Venus. They showed that its atmosphere is filled with corrosive gases, thick clouds and very high winds. Recent European Vena Express, which was landed about 10 years ago, lasted a few years ago, it was dedicated to atmospheric and plasma investigation. It has revolutionized our understanding of the atmosphere of Venus. What we are interested in the surface and subsurface, which can be proved by radio waves. The Magellan spacecraft launched around Venus has been highly successful in proving the surface of Venus by radar echoes and a radiometer. By radar, it gets reflected by the surface. The radiometer, you get the radio wave from the surface. Like you get radio waves coming inside this room also. Penetrate. Magellan used its high gain antenna to measure radar backscatter. Passive microwave emission at 2500 MHz, 12 centimeter, not meter waves. Resulted in topographic map which I will show you. Mapping of planet has revealed a surface dominated by lowlands and also extensive volcanic and tectonic information. This is very interesting. The green and blue areas correspond to the lowest elevation. 90% of surface lies within an altitude range of about 3 km. Surface is dominated by smoothly rolling plains. Ishtatara is the highland area with highest mountain, about 11 km high. This is from the topographic map made from the radio observations of 12 centimeters. Well, emissivity depends upon temperature into emissivity gives the brightness temperature. So that's important information. How does the emissivity varies across the surface? So, global emissivity map of Venus by the Magellan orbiter, longitude to 60 degrees, they did a fairly good job. Sparse color emphasizes surface details within the emissivity interval 0.8 to 0.9. But this is emissivity from the surface only, not from below the surface. The 12 centimeter does not penetrate.
Surface is atmosphere or the ground?
Surface, ground of Venus. Atmosphere, I'll tell you. Well, microwave observations, which most of the microwave emission takes place from the atmosphere, not from the surface. Earth-based probing of Venus initiated, this is a summary of the whole thing. 1960 orbiter-based probing began in 1967. Earth-based probing of Venus, orbiter around Venus. CO2 dominated atmospheric thick clouds that was discovered rather early in the 60s. Microwaves greater than 7 gigahertz occur only from the atmosphere, not from lower atmosphere, because they get absorbed by the gases there. Allow probing is upper atmosphere, but less than 7 gigahertz can penetrate clouds atmosphere from surface and subsurface. Magellan, which I told you already, with microwave radiometer S-band, mapped 90% surface of Venus, single polarization frequency. VLA was used by Butler to probe the atmosphere and surface. Subsurface probing required observation longer wavelength. It is a grand summary of the microwave observation of Venus. This is a VLA observation.
Well, what was there in the right hand side?
There's a VLA.
No, the other previous slide.
Well, this
Schematic.
some new. Lot of details are there. Slow conducting cells, rising currents in equator, descending at poles. I got it from some Google. 10 to 50 kilometer atmosphere convectivity, stable grower, haze, zone, middle cloud deck, sulfuric acid clouds, ice crystal haze, ionosphere output 1000 kilometer. But ionosphere is very weak, so that was an explainable meter wave observation. We have discussed that also in the paper. This is the temperature on this side. 740 K surface, but it goes down as you go higher. It goes to 220 K only. So people are proposing to launch a satellite so that you can go and live there. Temperature similar to Earth. So at that height you can have a Venus, of course, a lot of interest by a lot of people. VLA consists of 27 antennas, each of 25 meter diameter. It's well known. Some of the people here may not know. You can see at the microwave, at the highest frequency, 22 gigahertz, you call microwave. It's featureless, so it's clearest from atmosphere, 50 gigahertz. By the time you come to 4.8 gigahertz, you start seeing some surface feature. So I showed to you Magellan and a lot of surface feature. Magellan did detailed mapping from orbiter on the Venus. And this is the result of VLA observation. It's important. This is the 1, 2, 3, 4, 5, 6 frequency that VLA measure. The brightness temperature, which I said to is related to emissivity, rises down in your fashion. 21 centimeter, 2 different observations done 2 different days by VLA. It drops down. But as I will show you, Butler et al. In a detailed paper tried to model these observations. And they concluded that, well, these are the observations made in 1970 using a Micrometer et al. Using, I think, Caltech OS Valley. This is 70 centimeter by Condon et al. Using RSC boat. And doubts were there in the literature that, well, these values may not be correct. And so nobody has, there were no other instruments which could do that except GMRT, these values. So Butler et al. Said that they cannot explain these observations, maybe calibration error. So we have discussed that also in our paper. Using Bars et al. Scale, etc. Calibration error cannot be responsible. And this is the model. It's not clear here, but the model fits exactly the observation. And at longer wavelength, they say it should be this. But they say they cannot explain these observations. So they using the VLA, they try to fit a model. The decimeter wavelength and meter wavelength radiation rises from surface, subsurface, but at microwave frequencies come from the atmosphere, which I said to you. So they consider two different temperature pressure profiles, derived from the Pioneer Venus probe and inferred from occultation experiment of Mariner 5. Butler et al. Consider SO2 profile as uniform at all latitudes, less than 40 km, and S2SO4 profile with non-zero value between 37 and 51 km. That's from the literature estimated as a microwave outcome. This is the result. So these are their measurements with error bars. They consider different contents of SO2 and S2SO4 to explain the microwave observation. And if you look at here, 505, 499, 565, 561, 657, 645, 679, 680, 687. But by the time we come to 1.4 gigahertz, 612, the value is high according to their model. So they could not explain this, but that's what they said is the content of the atmosphere. This of repeating the real observation, vertical values is square boxes, but disagrees at lower frequencies. According to this, basically we are doing a forward consideration of subsurface contribution. We say GMRT observation with longer wavelength help to probe deeper subsurface as described next. My talk is short, it's not very long. Well, I suppose everybody knows GMRT. The talk I have to describe. Kandu wanted me to talk all about genesis of GMRT, genesis of radio astronomy. Maybe I should have done that. You can do both. You can do that even now. Someday, okay. I've written down here and there, but not made a PowerPoint on that. GMRT consists 30 and 45 meters. It was conceived after lots of whiskey. First January 1984. That's internationally known.
Yes.
And, that's it. I can describe it later how GMRT was. Somebody asked a question. Consider 30 and 45 meters. Located in an array of 25 kilometers. 14 antennas are located 14 actually in the central array, including some just outside, and 16 in the wide array. The 10-hour observation we get maps as it made with a perfect 25-kilometer dish. And I described that to Prof. Chandrasekhar. He wrote in our visitors book, shouldn't have thought that such thing can be done. He didn't know the cleaning and the radio astronomers how they clean the maps using non-linear, using 3 antenna phase. So like our visitors book was a shouldn't have thought such thing can be done. This is 92, where he wrote in visitors book. 14 kilometers. Consists of an array of 30 antennas, which I repeated, operating at 150 megahertz, 240, 325, 610, 1400. So now is a Yashwant Gupta and colleagues are trying to do 150 megahertz to 40 megahertz, more or less continuous upgrading GMRT. This is very important. DCM has got some already papers based on that upgrade. But this is the GMRT antenna. It was what was conceived by the thin wire mesh. Wind passes through, but radio wave gets reflected. And the problem was, how do you support the thin wire mesh? How do you provide a curvature? That's where we said the state mesh attached to democracy. Brightness temperature continues to go down. Unless it shows the TB values at 622 megahertz by rating, we propose that decreasing 10 in TB can be achieved by emission from deeper. Detailed modeling based on radiative transfer is being planned. As I explained earlier, the radio observation microwave arises from dense atmosphere Venus, the decimeter wavelength. Atmosphere is transparent, emission arises mostly from hot surface. The beta wavelength radio emission arises from its interior due to penetration depth of radiation that depends on real and imaginary component of dielectric constant, heat flow from the surface towards the subsurface. In order to explain our observation, we consider parameters of the interior surface that were not considered by previous photos. Well, this is a well-known equation. I could have used the derivation using electromagnetic theory. Depth of penetration is proportional to the wavelength. Real part of the dielectric constant inversely proportional to the imaginary component. Price for the penetration can be estimated very roughly at 10 days. Based on measured values of the real and imaginary parts of the dielectric constant, there is two Besson line that are measured of the real part of the dielectric constant. Measured values of thermal conductivity of Besson line here on fitted observation GMRT is described in the next slide. So what we considered was, we said radar observation showed that the dielectric constant looks like 4.5 radar observation with measure, etc. Real part is, imaginary part is not known. GMRT observation of polarization has to be made to find the imaginary component. Nevertheless, we can, to fit the model, we have to try different values of sun. But then, bigger question comes in. Does the heat flow? Surface is 735 K. So in our paper we submitted, we put a toy model saying we actually don't like it. So we said this regolith 4.5 is from the radar observation, and this is derived as assumed. This observation at 21 centimeter, this 600 megahertz, this 320 megahertz, this 230. So I just drew line like that and said, well, observation can be explained. But when we assume that temperature is not 735 yet, the temperature decreases inside. The question comes in, if there is a greenhouse effect, and temperature 735, let's say for million years, would the Venus get 735 below also? Not very clear. I tried to figure that out, not manage. How does the heat flow from the surface?
Do we know the thermal conductivity of the material?
Yeah, we can conduct it, I think,
From terrestrial material.
same as the terrestrial design. Thermal conductivity, if I remember, I had 2 watts per square meter per Kelvin. So we consider that in order to see how the temperature flows in this model. But then I tell you, we have another model. So this one rejected very clearly. So we requested the colleagues of Indian Space Research Organization, VSSC, Dr. Suresh Ayu and his student Tinu and Tilly, to work out a radiation transfer model which I described. This is repeating what I have said already. Radio waves have large, this is 5 slides are from Suresh Ayu. Radio waves have large penetration nice volume medium. Penetration depth is inversely related to frequency, emission low frequency emission from different layers. Subsurface information not available has to be derived. GMRT observation show decrease in white test temperature. To explain TB, the TB decrease, simulation based on radiative transfer of thermal emission, it can come. Preliminary results are. This is just a guess what? Temperature 750 K. To begin with, assume, say 500 million years ago, the surface temperature would have been of the order of 220 K, similar to Earth, or 340 K. You can figure it out from the standard equation taught in one of the early courses in astronomy. Take the sun and various planets, what's the brightest temperature? Is a question asked in interview. Calculate. Okay. So, but not greenhouse is not there. The surface input large amount of greenhouse gas. In the beginning period, large temperature gradient existed. That's what Tinu have made a diagram like that. But say in due course, it will be steady state. So, you think the temperature will be 735 below the surface. Emissivity depends on dielectric constant, which I have said already. Dielectric constant of Venus medium depends on soil and rock composition, which we do not know. We can only say what's the radar value, and this can be derived from there. Density, soil rocks, temperature insignificant in case of dry condition. I don't know why she put that. Dielectric constant emitted from observation by Magellan is 4.5 from radar. The imaginary part is not known. Penetration of radio waves is more than 10 times the wavelength into dry and low dielectric medium like Venus. Radiative transfer are essential. So in radiative transfer, what is done is you assume top layer is a 2 meter level like moon. Dielectric constant 4.5. Second layer solid rock. And then do a ray tracing. This is soil. Soil means it's a regolith, as it is called. It's broken rocks and soil. Moon is known. As I will say, we do not know how it comes from Venus. We think it exists there. These two media are constructed stratified with 3 layers. The model of 250 or 0.25 meters thickness having uniform physical property. Each layer attenuates, absorbs incoming radiation, emits this radiation, the local thermal equilibrium. The standard way of doing the equation. Radiation propagates towards the angle that is estimated. Indicative. These are results. So simulation from TV from GMRT frequency 1465 are made for a 2 layer. Stratified layer 125 is considered. Assume isothermal surface condition. 4.5, which I have said already, rock layer 8. The basalt, which Linera said, surface consists of basalt, and there are a lot of measurements on the basalt in granite on Earth. So one assumes the dielectric constant is similar to 8, from some 10-12 measurement mean value comes to the Earth, basalt in granite. This is therefore if we don't know whether polarization observation, we can have some idea of that. So this of course part of the radiation transfer model. These are results. So 4860 megahertz, 4.86 gigahertz, 4860 megahertz. Simulation is 653. Observed is 680 plus minus 14. 1465, 625, 620, 1385, 620, 612, 606. It's reasonable, but by the time you come to 330, is still not correct. So the more work has to be done in the RT model. It's only preliminary, indicating that it is possible by you considering the sublayer temperature is 750 only, or 735. One can, by doing the ray tracing, can explain the observation. So this is the conclusion. GMRT observations show that brightest temperature varies at meter wavelengths considerably lower than at centimeter wavelengths, indicating the radiation at long wavelength arises from deeper layer. The radiation transfer model shows good agreement at high frequency, dispatch at lowest frequency has to be investigated further. Two-layer RT model will regulate the 2 meter consider broken rocks is overgrown or solid rock. Conclusion: RT model combined with GMRT observation show that the top 2 meter layer of inner consider regulate consisting of solid rocks. 2 or 3 or 4, but it does indicate that the Venus surface is somewhat similar to that of Moon. In case of Moon, the regolith is caused by impact of meteorites. It's well known. The astronauts have been there. We know what the top layer is. For Venus, the top 2 meter layer may be caused by volcanic activity. So this is the summary results which Venus observation, GMRT observations is able to tell us about subsurface of Venus, which is not possible by any other direction. Thank you.